Hey everybody, we're going to take a look at this integral here. It's a math video, so there's no guitar stuff anywhere in this. So if you don't like math and you're not interested in it, just sit this one out, okay? But anyway, this is a famous integral called Ahmed's integral. Um, it has a surprising evaluation and shows up in a lot of unique places, and it's pretty tricky. Um, Flammable Maths did it. The YouTube channel Flammable Maths, this young German mathematician, evaluated it, and it took him several chalkboards, and it was evaluated in Paul Nayen's book and Inside Interesting Integrals, and it took quite a few pages. He had to introduce a another variable and differentiate with respect to it and come up with a differential equation and solve that. But anyway, well, I noticed something here with this, and I'm going to show you. I got pretty far with this using a simple technique, but I couldn't quite polish it off. And I'll show you where I run into trouble, and maybe you guys can help, any of you mathematicians out there. But anyway, so let's take a look at using Euler's strategy, and this is one of Euler's strategies for integrals. But there's this book called The Calculus Gallery by William Dunham. He wrote Journey to Genius, and here's this chapter on Euler. Euler was one of history's foremost integrators, and the more bizarre the integrand, the better. His works are filled with such non-trivial examples. So anyway, look at this one over here, right here. Okay, so this is the sine of the log of x over divided by log of x from 0 to 1. Notice that, remember, Ahmed's integral is from 0 to 1, and it has the same, there's a function on top, and the argument's the same as the denominator. Notice that. That's the same as what we have here with Ahmed's integral. So anyway, what he did was just expanded the top as an infinite series, and then the bottom, the denominator, just gets, subsumed up into the numerator of this infinite series, and just lowers the degree by 1. So then you just evaluate each one of these, and you end up with this. And of course, we all know that is pi over 4. Okay. So yeah, so here it is, pi over 4, which is, okay. So anyway, let's do the same thing here. Let's expand inverse tangent as an infinite series, just like Euler's method. So that's, the, right here is the, right here. We're going to expand it. It's very simple to do. You just expand the 1 over 1 plus x squared. Integrate that. Anyway, and then you will put in the substitute this for x, the square root argument, and then you just leave it in there. We're just sticking it in there, and then we divide by the same argument, just like. So that cancels, that goes to 1. This is just squared now. This goes out, and you're left with a 3 there. Then you got a 5 out here. This is lowered by 1. 1, 3, 5. Lowered by 1, that's 0, 2. Maybe I just found out where I went wrong. But anyway, and then you divide through by that last thing we have. We have 1 plus x squared. Just divide each term by that. And then this is a basic integral. Each one of these is just a basic thing. So we're just going to use Wolfram alpha. I know some people are just don't like it, but whatever. So here's Ahmed's integral, and we just you just evaluate each one. That first one, you just term evaluation of the integrals, okay, is what we're doing now. So you just distribute the integral out to each one of the infinite series. Okay, so that's equal to pi over 4. this next one, Wolfram alpha, gives 1 plus pi over 4. This next one, Wolfram alpha, gives 10/3 plus pi over 4. Then, etc., etc., etc. And so then we just, multiply this out and distribute the 1/3. So you're going to think about it. If you distribute out all these to the power, just think about the pi over 4s now. Okay, we have one here. 1/3 times pi over 4 plus, well, that's minus 1/3 pi over 4 plus 1/5 pi over 4 minus 1/7. And we do that forever, we're going to get pi over 4, and you factor out the pi over 4, you're going to have that Leibniz series alternating, with the odd numerals in the denominator, and you're just going to get that time, which is pi over 4 times pi over 4. So we're going to get pi squared over 16, right? We're just multiplying pi over 4 times pi over 4. See, this is what you get if you distribute it out, these 1/3, and just only looked at the pi over 4 term, okay? But so now we have to look at what we'll do. That's the first term, and so you wind up with this infinite series, and this is where I run into the problem. I don't know what to make of this weird thing, and I've been looking at my finite, what's it called? Oh God. Finite derivatives. Oh God, of course I'm having a brain fart right now. I can't think of it. Finite difference theory. That's it. Finite differences, and it can find the solutions to a lot of these. Like if this was a denominator was just 1, you can easily find. And I really mean easily find the sum of this, because it uses the psi function, which is that the derivative of the gamma function? I think it's... Anyway, there's a lot of... it winds up to be an evaluation of the psi function. The Greek letter PSI is what it looks like. I'm probably not pronouncing it correctly, but I'm trying to remember how my Greek professor said it a long time ago in grad school. But anyway, so I end up pi squared. So we know that by other methods that this integral is equal to pi squared. It's equal to 5 pi squared divided by 96. So what we have here is we have pi squared, and this should equal pi squared over 96. This, it has to, because of the way, because we know Ahmed's integral is 5 pi squared over 96, and we have this first part, which is pi squared over 96, just by subtraction, we know this has to be pi squared over 96. So if you know how to get that out of this weird, see, it's just like a weird collection. If you know how to sum this infinite series, which is really just all these integrals evaluated. See, this is x squared plus 2 over 1 plus x squared, and then this is to the second power, then to the third power, and you just keep going. But it gets too big before you can find the pattern. It gets out of the my comfort zone, as far as the whole numbers, before you can kind of like decipher the pattern here. So anyway, this is just an integral I've been working on, and it works out real nicely, and this shortens up. I mean, the other guys took like pages and pages to evaluate this thing, trying to do other crazy methods and substitutions and all this. But look, if you just use Euler's technique, it just falls right apart. Especially with Wolfram alpha really helps. But this last little part, I just cannot kind of, finish her off here. So if you got any clues, let me know. I'd appreciate it. All right, take it easy. Adios.